Now it's the turn of Professor Cristobal Corral. It's an honor to present Professor Cristobal Corral, who will talk about the topological terms and Misner string entropy. He's from the Universidad Arturo Prat. So, Profesor Corral tiene 15 minutos a partir de ahora.
Thank you very much, Mauricio, for the introduction and for giving me the opportunity of presenting this work, which is called Topological Terms and the Misner String Entropy. This work is based on this preprint archive, which was done in collaboration with Luca Ciambelli, Jose Pablo Figueroa, Gaston Giribet, and Rodrigo Olea. And today we have we get the reply from Physical Review D that it is accepted. So we're super happy about that. The outline of this talk is, first of all, I will give a brief introduction about top nut and bolt in ADS, and how does the Misner string arise in this framework. I will comment briefly on the conserved charges using the Netherwell formalism, because Pablo already gave this super nice introduction, so I will go fast in this part. Then we will see that some problems arise in this framework, namely that the entropy coming from the Misner string is divergent, and therefore we need to renormalize it. And we will use the method of topological renormalization, and I will present the conclusions and further remarks. So general relativity is the best theory of gravity that we have so far. It can be formulated through the Einstein-Hilbert action, which is written here. It is a theory that it is invariant under diffeomorphisms and local Lorentz transformations. And it considers only one dynamical field, that it is the metric, and performing stationary variations with respect to the metric, we end up with the Einstein field equations in presence of the cosmological constant. These are field equations of second order in derivatives of the metric, and there are some well-known solutions to these field equations. I'm sure that you are solution, Friedman, Lemaitre, Robertson, Walker metric, and there is a plethora of exact solutions known in this theory. One of them that is quite interesting is the tau nut and bolt solution in ADS. This was actually the first attempt to get a stationary metric in GR by introducing an additional parameter, which is known as the nut charge. This is the N in here. I will treat the Euclidean version. However, the Lorentzian one can be obtained by performing the analytical continuation of the Euclidean time and also of the nut charge. So there are some interesting things to mention about this solution. The first one, if you look at the area coordinate in this case, the area coordinate becomes 0 when r is equal to n. One can impose some regularity conditions that I will discuss in a moment. But another interesting thing is this off-diagonal term that appears here. And actually, if you if you perform or if you study the asymptotic behavior of this solution is neither asymptotically flat nor asymptotically ADS, mainly because of the presence of this nut parameter. So there is an off-diagonal term in the asymptotic region, and it is proportional to the nut charge. So in this case, this parameter, the nut charge, enters in the characterize the asymptotic behavior of this solution. There are two parameters in this case, which is this m, this integration constant m. G is related. G is the Newton constant, and this L is related to to the cosmological constant. L in this case is the ADS radius. This is the solution, and it is continuously connected to Schwarzschild ADS in the limit when the net charge goes to 0 in the Euclidean regime, of course. And so we can make this solution completely regular by imposing the following conditions. The first one is the condition for the nut, namely that the metric function vanishes at r equal to n. And moreover, in order to have absence of conical singularities, we impose periodicity on the Euclidean time, which is given by this beta. And this beta, of course, in the approach of Hawking, is the inverse of the temperature of the solution when we go to thermodynamics. And for the Bolt, on the other hand, Bolt, it is a solution characterized by an horizon. So in this case, the metric function vanishes when R is equal to RB. And as in the case of the knot, imposing the absence of conical singularities, we have this relation between the derivative of the metric function evaluated at the Bolt radius, and this is related with the inverse of the period of the Euclidean time. These two conditions fix the integration constant m in terms of the net charge, as you can see in here in this equation. This is the condition that you get for the nut, and for the Bolt you get a similar restriction. But now we have here the Bolt radius, and it is worth mentioning that in this case the Bolt radius is bigger than the nut charge. Another interesting feature of this solution, when you take this case, the nut, when the mass is related with the nut charge in the following way, the Weil tensor is globally anti-self-dual or self-dual depending on the sign of the nut charge. And this is similar to what happens with instantons, with self-dual instantons in Yang-Mills theory. And moreover, the Pontryagin density associated to this geometry is non-vanishing. This is different to what happens in Schwarzschild, in Euclidean Schwarzschild. And so this is the Pontryagin density in this case, and somehow it portrays topological inequivalent vacua, which are labeled by the nut charge. And so since this solution is a regular solution to the Euclidean Einstein field equations, in the case of the nut, it is globally self-dual or anti-self-dual. It has a non-trivial Pontryagin density. Usually the people say that this class of solution are the gravitational analog of instantons in Yang-Mills theory. There is an interesting observation done by Misner in the 60s that if you choose orthonormal frames in the following way, you can show that the time differential can be written in the following way. So you can see here that there appears two obstruction to foliation to the space-time in this coordinate-independent fashion. For instance, let us look at the first one, and there appears an obstruction to foliation with hypersurfaces of constant time when the metric function f vanishes, similar to what happens with the horizon of black holes. But additionally, there appears an additional term, as you can see here, that it is proportional to the net charge. So in the limit when the net charge is 0, this term is absent. And moreover, there appears an additional obstruction to foliation when theta is equal to 0 or when theta is equal to pi. And as was shown by Hawking and Hunter, this obstruction to foliation generates entropy. And therefore, this kind of singularity, this coordinate singularities, it is a string-like singularity, similar to what happens in the magnetic monopole with the Dirac string. Actually, n is interpreted as the magnetic mass of the solution, and therefore, in the case when m goes to 0 and n is different from 0, this solution represents the gravitational analog of a magnetic monopole. And so this was shown by Misner, and due to this, this class of string-like singularity along this axis is known as the Misner string. Misner has shown that this string-like singularity can be moved by choosing a proper coordinate transformation, as you can see here. Indeed, choosing plus or the minus in this part of the metric, the position of the Misner string can be moved to the North Pole or to the South Pole, respectively. And therefore, since... Sorry? How many?
5 minutes left.
Okay, so I will be brief. So since the position of the Misner string is a coordinate artifact, this leads to the people to think that the position of the Misner string is unobservable. And so if you would like to get rid of this string-like singularity, there is a relation between the time coordinates, and this imposes that the time coordinate has to be periodic. And this is a problem in the case of the Lorentzian signature, because there will appear closed time-like curves, and we will have some problems with causality. However, there are some recent works that they shown that for a observer following geodesics, actually the Misner string is transparent. So I will focus anyway in the case with the Euclidean signature, and the conserved charges can be computed using the nether-world formalism, as Pablo explained us in his very nice talk. And so the main component that we need to compute is this 2 form, which is known as the nether prepotential. And in the case of GR, this E tensor is the functional derivative of the Lagrangian with respect to the Riemann tensor. And so you introduce this here, and psi is the Killing vector associated to the Euclidean time isometry. And so what Wald shown in his well-known paper is that the entropy of a black hole is nothing but evaluating the nether charge at the horizon. However, this is not the only obstruction to foliation that we have in tau naught. We also have the contribution coming from the Misner string. And in this case, we have additional components, as you can see here. And to compute the nether charge in this case, we integrate the nether charge at the horizon. In the case for volt, in the case for the knot, this integral is 0. But the contribution coming from the Misner string, that comes from the 2 terms, actually renders that the usual relation between the entropy and 1/4 of the area of the black hole doesn't hold in tau naught. For asymptotically locally flat spaces, this was computed using the Wald formalism by Garfinkel and Mann in this nice article, and they found the same result as Hawking and Hunter and Page. However, the latter used an infinite background subtraction. This case is covariant. However, you can recover the result of them by subtracting these 2 things. However, if you consider asymptotically locally ADS spacetimes, the contribution of the Misner string becomes divergent. So we need a prescription to renormalize the entropy coming from the Misner string. And this is the main message of this talk, that this can be done by introducing the Gauss-Bonnet term. This the renormalization of conserved charges by using topological invariant was first proposed by Rodrigo Aros, who is in this audience, Contreras, Olea, who is also here, Troncoso, and Zanelli. And the nice thing is that we can use the same prescription, and even though the asymptotic behavior of tau naught is characterized by the naught charge, the same prescription can be used here to regularize the entropy coming from the Misner string. Even though the Gauss-Bonnet doesn't change the bulk dynamics of the metric, it changes the nether charges, as you can see in here. It changes the E tensor, and so the field equations can be solved by Einstein spaces in the following way. And as you can see here, the nether prepotential is given by the following expression. Now you can see here that we have the Weil tensor, and the Weil tensor has the proper falloff in asymptotically locally ADS spacetimes. However, we have this annoying term that is the one that produces the divergences in asymptotically ADS spacetime. So the nice thing is that introducing the Gauss-Bonnet term allows us to fix alpha such that this term is absent. And this choice of the Gauss-Bonnet term renders the Euclidean on-shell action equal to the McDowell-Mansouri action, that it is an interesting proposal to treat gravity as a gauge theory. Using this coupling constant, we can compute finite entropy using the Wald formalism. We can also compute the Euclidean action, which is given here. And also from the Euclidean action, you can compute the energy of the solution. And we also check that starting from the Euclidean action and using the standard method, we obtain the same entropy as we got from the Wald's formula. And this energy that it is in here, it is exactly the same energy that we have by imposing regularity conditions. These quantities satisfy the first law of thermodynamics, and they satisfy the Gibbs relation down here. So this is the summary of my talk. I think that I am running out of time, so I'm not going to repeat this, but some further remarks. We also consider the case when the Chern-Pontryagin invariant is included, and this option fixes the tau-NUT solutions as the reference background. So all the thermodynamic properties of this spacetime are measured with respect to the tau-NUT solution when the Pontryagin density is included. This method is equivalent to the counterterms of Balasubramanian-Krauss and to the counterterms of Empire and Johnson-Myers, since these are equivalent at the spatial boundary of ADS. However, the main advantage of using this is that this formalism is covariant, it is background independent, and actually it adapts in a suitable way to regularize the contribution of the Misner string. Before finishing, I would like to give an advertisement. My colleagues and I are super happy because we recently got accepted our master in physical science at our university. So we are looking forward for a bachelor student who are looking for a program to continue their studies. So you can take a look for further details in this link over here. So this is all that I have to say, and thank you very much.
Hey, thank you, Cristobal, for your nice and clear talk. It was very interesting. So, is there any question for Cristobal? Is anyone want to ask something for Cristobal? Well, yeah,
maybe
Carlos.
Okay, thank you. Hi, Cristobal. Congratulations for your accepted paper and the Magister. It's also a nice talk. Thank you very much. I was thinking on the regularization method that you showed. I'm not an expert on gravity, so I would like to know what is exactly what you are doing when you put these terms? It seems that you modify some quantities on the boundary, right? I would like to know what kind of modifications can you include? It's any boundary term or has to satisfy some property?
Excellent, Carlos. Thank you very much. So in this case, the Gauss-Bonnet is actually related to the Euler invariant plus a boundary term. Therefore, it doesn't change the conserved charge. It doesn't change the field equations, but it has a non-trivial contribution to the conserved charges. And this is the main message of this talk, is that by including this topological term allows you to fix the Gauss-Bonnet coupling such that the conserved charges in ADS become finite. And these charges are related to the entropy. When you integrate them in an hypersurface that obstruct you to foliate the spacetime with hypersurfaces of constant time, and this is related to the entropy. And so, the main message is that the topological terms doesn't change the field equations, but they do change the conserved charges.
Okay, but do you impose some, in quantum field theory, you impose the fields to some regularity in infinity of the fields. They have to decay. In gravity, is this the same? Is this a good boundary term? Only
yes. Yeah, somehow, as I was showing here, let me go. Yeah, in this case, for instance. So the Weyl tensor has the proper fall-off in this case. So this goes to 0 as r goes to infinity. But this is not the case for this term that you have here. And introducing the Gauss-Bonnet allows you to fix alpha such that the divergent term is absent. So this is the...
Thank you. Yeah. Excellent, thank you.
You're welcome.
Okay, so Mauro, do you have a question?
Yes, thank you, Cristobal, for your talk. I wanted to ask about why do you focus on the parity preserving terms or sector?
Excellent, Mauro. Actually, we considered the other one. So we included the Pontryagin one. So for the sake of time, I didn't include it in my talk. So we included the parity odd, which is the Pontryagin in this case. And the message that I could give is that the implication of including the Pontryagin invariant is that it changes also. Okay, let me put it in this way. The Pontryagin, the coupling of the Pontryagin, it is not fixed by regularity of the conserved charges. And therefore, you need another criteria to fix the coupling of the Pontryagin. And in this case, the criteria that we use is to choose that parameter such that when you evaluate the Euclidean action, the entropy, or the energy in a self-dual or anti-self-dual solution, those quantities vanish. And this is the criteria that we use. And in that case, that is the reason why including the Pontryagin term, which is parity odd, as you mentioned, changes the quantities and fixes the tau naught solution as the reference background in this case.
Okay, thank you very much.
You're welcome.
Okay, so we have a last question from Rodrigo.
It's not actually a question. I want to complement the answer by Cristobal on Carlos Marat question, because this is a very long story dating back by the time of my PhD thesis in 2000. We added this topological term, and you have the right to think that it modifies from the point of view of the boundary dynamics. It completely modifies the theory because it doesn't affect the equation of motion, but a physical theory is not only about the equation of motion, it's about the whole package of conserve quantities and boundary terms and boundary conditions. It's really strange. It took us long to realize that if you add this sort of terms, what you have added at the boundary is inconsistent from the point of view of the boundary, in principle. Because if you split the space-time in, let's say, 3+1 dimensions, you get variations. You rely on physical theory, like in classical mechanics, that is delta Q at the boundary, delta of the coordinates. But here you get delta Q and delta Q dot. So you have variation of the extrinsic curvature. And there is no way of getting rid of the variation of this extrinsic curvature. There is no way to go back from Einstein-Hilbert plus topological term to the classical mechanics description. There is no way to define the Dirichlet problem for the metric. So what saves the day, and it took us long to realize, is that in asymptotically ADS spaces, there is an axiom that the extrinsic curvature is proportional to the boundary metric. And at the end of the day, you define a proper Dirichlet problem, but on a metric that is defined at the conformal infinity, because variations of the metric are the same as variation of the extrinsic curvature. And that's the reason why we ended up putting this in a holographic context, because otherwise it would have been inconsistent. There is no way to define the Dirichlet problem with topological terms in 4 dimensions.
Thank you very much, Rodrigo.
Okay, so I think we are done. Thank you again to Cristobal. It was such a nice talk, and congratulations for your accepted paper. Thank you very much.